All right, so we have 5 cards to choose from. 2 of them are aces. We're going to select 2 cards total, 1 at a time. So probability of A is the first card selected is an ace. So what's the probability that I pick an ace? In the chat, or unmute, or throw me some fingers.
1/5.
Not 1/5. There.
2/5.
2/5. Thank you, Piper, and thank you, Joanna. I just saw your answer in the chat. So 2 out of 5. All right, and then I put it back. I shuffle. What's the probability that my second card chosen is an ace?
2/5.
Thanks, Chloe. 2/5. All right, so this time we're going to do it without replacement. So I shuffle. What's the probability that I pick an ace?
2 out of 5.
Thanks, Chloe. 2 out of 5. And this time, no replacement, so that card is gone. What's the probability I pick an ace?
1 out of 4.
Thanks, Chloe. 1 out of 4. So, the first one is what we're going to focus on today, because when we draw 2 cards with replacement, we can say that events A and B are independent, meaning that the occurrence of the first event has no effect on the chance that the other will happen. So with that first way of drawing it, I drew an ace, I put it back. So the fact that I got an ace for my first card had no effect on the probability that I got an ace for my second card. When I kept the card out, the probability that I got an ace for my second card was changed by the fact that I got an ace for my first card. So with replacement, made events A and B independent. When I did without replacement, they are not independent. So when we did the above problem with replacement, the probability of B given A was the same as the probability of B. So when events A and B are independent, the probability of B given A, sorry, I wrote the wrong thing here. I wanted to give the actual number, 2/5. Probability of B given A is the probability of B. I was trying to save it for the second one, sorry. This right here is going to be the key to independence. That is how we prove 2 events are independent. So when you're asked, are events A and B independent, yes or no is not a complete answer. You have to say yes, because probability of B given A equals the probability of B, or no, because the probability of B given A does not equal the probability of B. So this right here is how we show independence. And I will go over examples of how to do that, but this is the key to showing 2 events are independent. And you can flip it around. It means the exact same thing, but sometimes seeing the letters in different orders kids go, oh, I can use different, I can do B given A or A given B. Biggest thing, notice that the front event here is the one that we want to show. We want to show that A happening had no effect on B. So B given A happened is the same as B, whether or not A happened, or vice versa. A B is the same as A. On Friday, we learned our general multiplication rule that would help us find the probability of A and B. And that was the probability of B given A times the probability of A. And today we're going to get a little more specific and have our multiplication rule for independent events. So when two events are independent, probability of B given A is equal to just the probability of B. So we can simplify this multiplication rule and say that the probability of A and B comes from the probability of B times the probability of A. And this is our multiplication rule for independent events. Multiplication is a really long word, and every time I write it, I don't know why it doesn't feel that long when you say it, but when I write it, it's actually quite long. Sorry. Just the weird thoughts that your math teacher has as she's spelling things. So this is a P, kind of looks like a D, sorry. So we are going to be focusing on proving two things are independent or not. Obviously, they're not always going to be, yes, they're independent. And then we're also going to talk about using this rule when we're looking at independent events. And then we're going to finish up by talking about whether events are mutually exclusive, independent, both, or neither. Any questions before I flip to the next page? I'm so jealous of Shahar right now. She's outside. I'm stuck in a windowless classroom and she's sitting out in the sun. It's not fair. All right. So like I said, we're going to start out by showing whether events are independent or not. Justification is the math. So probability of B given A equals, oops, close my parentheses, equals the probability of B. That means they're independent. If I can't show that, I get they're not equal, then they're not independent. I suppose you could say dependent. Statistics is one of those weird things where we focus more on the negative, the contrary, not independent. We don't say dependent. All right, so we're going to be talking about cards in the first two, and then we're going to move to a different type of situation. I want to draw a line here because last period it bothered me that there wasn't a line between them. It seemed very, I don't know, just bugged me. All right, so first one, we're going to shuffle a standard deck of cards. We're going to turn over the top card. We put it back in the deck, shuffle again, and turn over the top card. Event A, the first card is a heart, and event B, the second card, is a heart. So we want to see if A and B are independent. So we want to see if B given A is the same as the probability of B. So B given A. I have my deck of cards. I I can't shuffle that way. I have to actually shuffle. I was just trying to do it without making noise. Shuffled my cards. I turn over the first card. Hey, it actually is a heart. That was pretty cool. So A happens. I put it back in. I shuffle again. What's the probability that this card is a heart? Either throw it in the chat or throw it in the chat or unmute yourself. Sorry, I interrupted you
13
guys.
out of 52.
Say it again.
13 out of 52.
Perfect. Thank you, Chloe. All right, so probability that this top card is a heart is 13 out of 52, even though A happened, because I put my top card back in there. That 4 of hearts went back in, which meant I still had 13 hearts, and I still had 52 cards total. Now, what's the probability that my second card is a heart, regardless if A happens? So I've shuffled, I flipped my top card, it's a club instead of a heart. I put it back in, I shuffle again. What's the probability that this top card is a heart? How many hearts are in the deck? $13. How many cards are in the deck total? 52. So even though A didn't happen, the probability that B happens is still 13 out of 52. So in this case, events A and B are independent. Any questions about that one? All right, so still working with cards. So we're going to shuffle our standard deck of cards. We're going to turn over the top 2 cards one at a time. Define events A, first card is a heart, B, second card is a heart. So I have my deck of cards, shuffle them. Shuffle them, shuffle them, shuffle them. So we want to see if the probability of B given A is the probability of B. So I shuffled. I'm going to turn over the top 2 cards one at a time. So my top card is a heart. So A happened. What's the probability that this next card is a heart? How many hearts are left in the deck? I took one out, so how many are left? 12. And I have one card out, so how many cards are left? 51. So the probability of B given A happened is 12 out of 51. Sorry, Joanna and Emma. I checked and then I started talking. I should have double checked. Thank you. All right, so then I put, we're gonna try this again. Oops. So I flipped my first card. It's not a heart, so A didn't happen. What's the probability this card's now a heart? How many hearts are in the deck still? Thank you, Emma. 13 out of 51. I still have 13 hearts. I only have 51 cards. So in this case, The probability of B given A is not the same as the probability of B, and A and B are not independent. Now, of course, cards are not the only type of questions you need to be able to determine independence with. So we're going to look at a two-way table for this one. The 28 students in Mr. Tabor's AP Statistics class completed a brief survey. One of the questions asked whether each student was right or left-handed. The two-way table summarizes the class data. Choose a student from the class at random. The events of interest are female and right-handedness. Now, for some weird reason in this table, they didn't list gender as female and male. They listed them as A and B. So there is a little note that gender A really means female and gender B means male. So I'm going to put an F in parentheses. This is female and this is male. I don't know why. I stole this from the textbook. I don't know why they use A and B. It would have been hard to put F and M, or even use the little symbols for female and male. Female, male. All right, so we're interested in female and right-handedness. We want to determine if the two events are independent. So we can show probability of female given right-handedness. We want to see if that's the same as the probability that a student is female. Now, with the previous two, it said first card, second card, first card, second card. So we knew that we had to do B given A. Here, it doesn't say anything. So if you wanted to, you could do the probability that they're right-handed given they're female and see if that's the same as the probability that they're right-handed. There is no specification about the order here. Notice the first one in the given, the conditional probability is the one that we're looking at by itself. First one in the conditional is the one we look at by itself. I do it this way because I see female and right-handed and my brain just puts them in that order, but you can do it this way. Now, you don't have to check both, okay? And if this one doesn't work, unless you made a mistake, this one won't work. And if this one works, this one will work. So they either will both be true statements or they're both going to be false. You don't need to do both. You can do one or the other. I'm going to do this one. If after I'm done with it, you guys want to see this way, we can do it this way. So, even though we read it as the probability of female given right-handed equals the probability of female, I'm going to start over here because that one's a little more straightforward to me. So what's the probability that a student chosen at random is female? I know there are 28 students in the class, so it's going to be out of 28. And then gender A is female, and there are 3 plus 18. There's 21 females in the class. So probability the student I randomly pick is female is 21 out of 28. Then for female given right-handed, so I'm given that they're a right-handed student, which means that I am looking at this row. And I need to know the total number of right-handed students in this class. 18 plus 6 is 24. So it's out of 24 because I'm given they're right-handed and there are 24 right-handed students. Of those 24 right-handed students, 18 are female. So female given right-handed is 18 out of 24. Now some of you may type that into your calculator and automatically get decimals. I'm more of a fraction person, so I'm going to simplify. 18 and 24 are both divisible by 6. 18 by 6 is 3, and 24 divided by 6 is 4. 21 and 28 are both divisible by 7. 21 divided by 7 is 3, and 28 divided by 7 is 4. So the probability that the student is female, given they're right-handed, is the same as the probability the student is female. So female and right-handed are independent for this situation. Now, do you guys want to see it the other way as well? Okay, I'm seeing yeses, head nods. So we'll look at it that way as well too. So on this one, we're going to do the probability that the student is right-handed given they're female, and see if it's the same as right-handed. So I'm going to start with this one because that seems more straightforward to me. So from doing it this way, we know there are 24 right-handed students, and there are 28 students total in the class. So the probability the student is right-handed is 24 divided by 28. For right-handed given female, so we're given the student is female, so we're going to look at the female total, which is 21. So this is out of 21. And of those 21 females, 18 are right-handed. So this is 18 out of 21. And again, you can type it into the calculator. You can see that the decimals are equal. 18 and 21 are both divisible by 3. So 18 divided by 3 is 6, and 21 divided by 3 is 7. 24 and 28 are both divisible by 4. 24 divided by 4 is 6, and 28 divided by 4 is 7. So no matter which way I wrote my conditional, I should get that they are independent. Up here, it was first and second, so I said B given A because obviously second would have to happen after the first. But if there is no specification on order, it should work either way. Any questions before I move my paper up? No? All right. So on this one, working with a two-way table, I like to draw in the little lines. My brain works better when everything's in its own special box, but you don't have to. So we're looking at a two-way table. Across the top, we have high school graduate, not a high school graduate. Going down the side, we have homeowner, not a homeowner. And then on this two-way table, the totals are filled in for us. So I'm assuming this was a survey, and 500 total people were surveyed about whether they graduated high school or not, and whether they own their home or not. So what is the probability that a randomly chosen person is a high school graduate? Somebody want to unmute, throw it in the chat. What's the probability from that table that a person graduated from high school? Thank you, Joanna. We have 310 high school graduates out of 500. Which 62, I think. oops, not negative, delete that, 0.62. And I suppose I should, because in a minute we're going to do conditional. So I'm going to call this high school, and this would be a high school complement, so not high school. And then home and home complement. And you'll see in a minute we're going to focus on high school and home, so that's why I chose those ones not to be the complements. So in question 2, it says if we know that a person owns a home. So we're given a condition here. They own their home. What's the probability the person is a high school graduate? So what's the probability they're a high school graduate given they own their home? Anybody want to try that one? What's the probability they graduated from high school given they own their home?
$221 out of 500?
221 is correct, but we're only looking at homeowners because we're told they own their home. So how many people said they own their home? Thank you, Nevaeh, and thank you, Emma. So we're told they own their home, and there are 340 total homeowners. And out of those homeowners, 221 graduated from high school. So that's 0.65. So what do our answers from 1 and 2 tell us? Well, besides the fact that they tell us the probability that one of these 500 people graduated high school, or the fact that they tell us the probability the person graduated high school knowing they own their home, they tell us that the two events are not independent, because here, this is the probability of high school, graduating from high school, and this is the probability they graduated high school given they own their home. If they were independent events, these two would be the same, but they're not. So the two events, graduating from high school and owning a home, are not independent. Because probability of high school given home does not equal the probability of high school. We know those two events are not independent. Number 4 says if we know that a person is a high school graduate, so we're given our condition, they graduated from high school, what's the probability they own their home? So what's the probability they own their home given they graduated from high school? Anybody want to try that one for me? Thanks, Emma. So we're given they're a high school graduate. There are 310 high school graduates in this table. And of those 310 high school graduates, 221 own their home. So 0.713. So why didn't we get the same answer for 2 and 4? And no, it has nothing to do with independence. Here, independence was the focus because we were looking at high school given the home with just high school. Here it's high school given home ownership, or home ownership given they graduated from high school. So we would not expect to get the same answer because these aren't asking the same question. So they're two totally different conditional probabilities. So we would expect that we would get different answers. Any questions before we move on to making fun of baseball? No? Alright. I'm not really gonna make fun of baseball, but I am. And I have a typo. It's not a bad one, but it's one. Alright, so in baseball, a perfect game is when a pitcher doesn't allow. I don't know why I put all. Actually, I do. I was tired when I typed this. I should say allow. So in baseball, a perfect game is when a pitcher doesn't allow any hitters to reach base in all 9 innings. And I really dislike that statement or definition. It's not just the pitcher, it's the other people playing the game too. So no hitters reach base in all 9 innings. Historically, pitchers throw a perfect inning, an inning where no hitters reach base about 40% of the time. So, to throw a perfect game, a pitcher needs to have 9 perfect innings in a row. And what's the probability that a pitcher throws 9 perfect innings in a row, assuming the pitcher's performance in an inning is independent of his performance in other innings? So really, we want to find the probability that a perfect game is thrown. And the probability that a perfect game is thrown comes from the probability that you have a perfect first inning and a perfect second inning and a perfect third and a perfect fourth and a perfect fifth and a perfect sixth and a perfect seventh, and a perfect eighth, and a perfect ninth. And notice how I have and in between. Perfect first, and second, and third, fourth, fifth, sixth, seventh, and a perfect eighth, and a perfect ninth. Since I'm looking at ands, and it tells us that we can assume independence. That means we get to use our new multiplication rule for independent events. So the probability of A and B comes from the probability of B times the probability of A. So to find the probability that it was a perfect first inning and a perfect second and a perfect third and fourth and fifth all the way through the ninth, I get to take the probability of a perfect first times the probability of a perfect second times the probability of perfect third times probability of a perfect fourth and fifth 6th, 7th, 8th, 9th, and the probability that an inning is perfect is 40% of the time, and we can assume that the probability the second inning is perfect has not been affected by the probability of the first inning being perfect. So that means each of these is 0.4. I suppose I can actually write out 0.4 9 times. That's 4, 5, 6, and I'm sure some of you are like, seriously, come on, Ms. Woodall, that's what exponents are for. You can write this as 0.4 to the 9th. I think I have 9. And no, you do not need to show this if you have a question like this on your homework. I just wanted to show it for the first time to show why we can use our new multiplication rule for independent events. If this was a question on your homework, you could write probability of a perfect game comes from 0.4 to the 9th power. I'd absolutely be fine with that. I just wanted to show why we can just multiply 0.4 by itself 9 times, because each of them are independent and our multiplication rule says we can. So 0.4 to the 9th, no plus sign at the end, is 0.000262144. Now I think this is one of the first times we've had a bunch of zeros at the beginning of our answer. Please go to the first 3 real numbers, okay? Oh, Nate threw in the chat, can't we do it with an exponent? I said that, I didn't see that, but see what I told you? You guys are like, seriously, why is she writing it out like this? Yes, use exponents. Like I said, just wanted to show where it comes from. So 0.000262. Please, I know I've said go to 3 decimals. Don't just give me 0.000 for an answer. Yes, I have had kids do that in past years. I want the first 3 significant numbers. I don't know if that's the actual definition of sig figs, so I don't call them that. But give me the first 3 real numbers. Don't just give me 3 zeros. You won't get credit for that. Questions before I move my paper up? All right. During World War II, the British found that the probability that a bomber is lost through enemy action on a mission over occupied Europe was 0.05. Assuming that missions are independent, find the probability that a bomber returns safely from 20 missions. So on this one, first of all, let's see, what color do I want to use? We'll use this one. Probability that they return safely would be the probability of lost complement. So lost and safe are complements in this case. So they could get lost or they could return safely. Now the probability we're given is that they were lost. So the probability they get lost was 0.05. We want to find the probability that they return safely. So we would do 1 minus the probability they were lost, and this would give us the probability that they returned safely. Oops, forgot to close my parenthesis there. So 1 minus 0.05 which would be 0.95. So the probability that they return safely is 0.95. Now we want to know the probability they return safely from 20 missions. So we're going to use what we just did before, because they tell us that we can assume missions are independent. So the probability that they're safe on 20 missions would be the probability they're safe on the first mission times the probability they're safe on the second, which would still be 0.95, 20 times. So we're going to do 0.95 to the 20th power. Which gives us 0.359. If I use a few extra numbers behind that 8 to round. Questions? This, by the way, if we were in person, would have been my check for understanding, but you guys get to watch me do all those now. No questions? All right. Number 2, government data show that 8% of adults are full-time college students and that 30% of adults are age 55 or older. Since 0.08 times 0.30 equals 0.24, can we conclude that about 2.4% of adults are college students 55 or older? Why or why not? So this right here is our general, our multiplication rule for independent events. So they're saying that probability that they're a full-time student times the probability they're 55 or older gives us the probability they're a full-time student and they're 55 or older. We cannot assume independence. Using this formula assumes it. If you can assume it, it's going to say it in the question, like up here in number 1. It says, assuming that missions are independent. Up here in the baseball example, assuming the pitcher's performance is independent. If it doesn't tell you you can assume independence, you cannot do it. So this right here assumes independence. This is the multiplication rule for independence. And we cannot assume that being a full-time college student is independent of being 55 or older. Aw, man, why didn't you guys tell me you couldn't see what I was writing? Sorry. Usually I check too, and that time I went, oh no, I'm fine. I have the paper up high enough. Next time interrupt me and be like, hello, we can't see what you're writing. So be careful of questions where it's just assumed. Like I said, the problems will say, assume that the missions are independent, assume that the pitcher's performance are independent. In statistics, well, eventually we'll learn a certain sample size that makes it big enough that independence actually doesn't matter. But for now, either it'll tell you you can assume independence, or you'll have to prove that they're independent. And if it doesn't say assume or you can't prove it, then you can't take it that the two events are independent. Are you guys good if I flip the page? Okay. So like I said, now we're going to finish off with looking at mutually exclusive versus independent. So we have 3 examples with 2 events each. We're going to determine if they're mutually exclusive, independent, both, or neither. So just as a reminder, mutually exclusive, I use me for the abbreviation. And mutually exclusive are 2 events that can never happen at the same time. So let's see. This is a really stupid one, but it's the one that came to my head. Playing basketball and scoring a touchdown. Those can't happen at the same time unless you're playing some really weird version of basketball. So that's just an example of mutually exclusive. And then for independent, we have to have a mathematical justification. We are going to look at whether B given A, the probability of B given A is the same as the probability of B. I start with mutually exclusive and then work through independent. So that's how I'm going to do the notes. That's not necessarily the way you have to do it, okay? So, we're working with cards again. These cards are, at least in my head, cards are something that even if I don't have a deck of cards, I can kind of like visualize it. So we're gonna select one, not on, select one, just one card, okay? From a standard deck. Event A, the card is red. Event B, the card is a club. So can I have a card that is both red and a club at the same time? Here's a club, in case you forgot. Can that card be red at the same time that it's a club? Clubs are black. There's no change in that. So A and B are mutually exclusive. My card cannot be red and be a club at the same time. So those 2 are mutually exclusive. Now we need to think about independence. So we want to look at if the probability of B given A happens is the same as the probability of B. So B given A, same as B. So if we look at the probability of B given A is a red card. So I know that my card is red. How many red cards are in a deck of cards? How many of my cards are red? guys thought I was being funny when I wrote down what a deck of cards is the other day, like twice in a row. Huh. There are 26 red cards in a deck of cards. Half are red, half are black. So I'm given that it's a red card. So my probability is going to be out of 26 because I know it's red. Now, out of those red cards, how many of them are clubs? Not a single one, because clubs are black. So the probability that B happens given A happened is 0 out of 26, or 0. Now the probability that B happened, whether or not, well, without A happening. So the probability the card is a club. There are 13 clubs out of 52 cards total, which would simplify down to 1/4. So the probability of B given A does not equal the probability of B, so A and B are not independent. Questions before I move on? All right, still working with cards, still only choosing one card from the deck. This time, event A, card is red, B, the card is a 7. So can I have a card that is both red and a 7 at the same time? I'm seeing lots of nods. Yes, I can have a red 7. Let's see if I can find one relatively quickly. I can. 7 of diamonds. I can also have a 7 of hearts. So in this case, A and B are not mutually exclusive because I have cards that are red and 7s at the same time. For independence, I want to see if the probability of B given A happened is the same as the probability of B. So if A happens, the card is red. That means I'm looking at only half of the deck, 26 of the cards. Out of those 26 cards, how many of them are 7s? Out of red cards only. How many of my red cards are 7s?
2.
2. Thank you, Chloe. And thank you, Emma. So then, probability that the card is a 7. There are 4 7s total out of 52 cards in a deck. 2 out of 26 simplifies down to 1/13. And 4 out of 52 also simplifies to 1/13. So in this example, A and B are independent. Any questions before I move on to our last one? All right, so still picking one card. Here, event A, still red. Event B, the card is a heart. So are A and B mutually exclusive? No, thank you, Joanna. They're not, because all hearts are red cards. So they are not mutually exclusive. For independence, we're going to see if the probability of B given A is the same as the probability of B. So A happened, the card is red, so I'm only looking at 26 of the cards, all the red cards. So out of those 26 cards, the red ones, how many of them are hearts? There are 13 hearts, 13 diamonds, 13 clubs, 13 spades. So if we're only looking at the red cards, 13 of them are hearts, and then 13 of them would be diamonds. And then the probability the card is a heart, well, there are 13 hearts. This time I'm looking at the full deck, not just the red ones, so it'd be 13 out of 52. That right there, we can see they're not equal to one another. So in this case, A and B are not independent. So in our first example, they were mutually exclusive, but not independent. In the middle one, not mutually exclusive, but they were independent. Here, not mutually exclusive and not independent. Now, I couldn't come up with an example where they were mutually exclusive and independent because those do not exist. You cannot have two events that are mutually exclusive and independent at the same time. Are there any questions before I tell you you are free to go?